Algebra 2, Lesson 13, Part A is about substitution. And I tried to make this substitution axiom a little easier to read in your notes than it might be in the book. It's still sort of long. So if two expressions, A and B, are of equal value, then A can replace B or B can replace A in an expression without changing the value of the expression, or in a statement without changing whether or not that statement is true or false, and in any equation or inequality without changing the solution. And you use substitution axiom all the time. Every time you're simplifying an expression, you take something longer and substitute a shorter way of writing it. Like if you had 3 plus 5, you'd replace that with 8. That's substitution. We're going to be using that same concept to solve what we call systems of equations, which is where we're going to have two linear equations in one problem, and we're going to be able to find out what one value of x and one value of y makes both equations true. So we're going to be using this, like I said, this axiom for that. And I didn't have the examples pre-typed for you, so let's go ahead and do example 1. There are going to be 3 on here. And we have x equals y plus 5. And the second equation, you put a big brace just on the left side of this, is to show that they're together. These are why I keep saying we need to use straight edges for the graphs and be very careful when we're graphing, because you actually could graph both of these and see where they intersect. And that would give you the same x and y we're going to get when we substitute. You'll see that later. So again, the first equation, x equals y plus 5. Next one is 3x plus 2y equals 5. All right, and so what we're going to do is, always for these, you look for a variable in either of these equations. It doesn't matter if it's x or y. So we're looking for a variable that has a coefficient of of 1. That has 1 as its coefficient. And you hopefully remember, coefficient is just the number in front of it. What's really nice is when they already have one of the variables all by itself, because that's what we need. We know that x equals y plus 5. We don't know what y is yet, but we know that it equals y plus 5. So we're going to take the other equation. Okay, we have this x. Here's the x in the other equation. We're going to put what x equals in place of it. So write the second equation, but instead of an x, we're writing in parentheses what x equals, y plus 5. And then finish copying this equation. 3x plus 2y equals 5. Now we have only one variable, and this will be easy to solve. Distribute, that's 3y plus 15 plus 2y equals 5. Now I'm adding like terms. 5y plus 15 equals 5. You know what? Probably only put 2 examples on here. So subtract 15. 5y equals negative 10. And then we divide by 5 and get that y equals negative 2. We need to find x and y. So now we're going to go back to this first equation that had the x already by itself. Okay, x equals y plus 5. Well, y is negative 2. So x equals negative 2 plus 5. That's 3. Now that I have that, I have numbers for both x and y, I'm going to, at least in my head, put these answers back into both equations, because this, in order to be a solution to this entire system, has to be the solution to both of these. It has to make both equations true. So if x is 3, that'd be 3 equals negative 2 plus 5. That's true. Now for this one, 3 times 3, that's 9. And then this is 2 times negative 2, so that's negative 4. So 9 and negative 4, that does equal 5, so I know this is right. And I'm going to write my answer as the coordinates of a point, because again, okay, 3, negative 2, x comes first. If we were to graph both of these lines on one graph, those lines would cross at this point. Okay, your book has 3 examples. I'm seeing that we only really have room for one more example in this page. So I think we will do, well, yeah, that one's good. Okay, so we're going to do example 2 from the book. You can look at example 3 on your own then, just for another example to help you out. So example 2, we have 3x minus y equals 11, and we have 2x plus 3y equals negative 11. Okay, so this is our system. And again, I look for a variable in either equation that has one as its coefficient. Okay, so not any of them. It's going to be this one. This is one I want to get by myself. If I use any of the other ones, I will have to work with fractions throughout my problem, and I'd rather not do that. So I'm going to take this equation, and I need to get this y by itself. I need a positive y equals. So 3x minus y equals 11. And you're used to getting y by itself by now. Okay, so we're going to subtract 3x. And that's, don't forget that negative. That is negative y equals negative 3x plus 11. Okay, I need a positive y. This is an understood 1, so I can, just like if that was a 2y, I'd be dividing everything by 2. That's a negative 1. I'll divide everything by negative 1. So that would give me positive y equals positive 3x minus 11. It just changes the sign of every term. Now, that y is going, that was from the first equation, so it's going to replace, we're going to substitute for this y in the second equation. So 2x plus 3 times, and instead of y, we're writing 3x minus 11 equals negative 11. And now we're going to solve for x. We're distributing again. 3 times 3x is 9x, minus 3 times 11 is 33. Add like terms. Add 33 to both sides. Getting a little sloppy. There we go. Okay, 11x equals 22. Divide by 11. X equals 2. Okay, then I go back here where I already have y by itself, and I put 2 in place of this x. Okay, so we're going to go y equals 3 times 2 minus 11. That's 6 minus 11, so it looks like y equals negative 5. Again, I need to make sure that 2 negative 5 works for both equations. And it's okay to jot that down when you're figuring it out. I think I'll do that this time. 3 times 2 is 6 in that first equation, minus negative 5 is plus 5. That does equal 11. And then in the, excuse me, in the other one, you have 2 times 2, that's 4, plus 3 times negative 5, so that's like minus 15. That does equal negative 11. Both of them work. I know I've got it right. If it didn't come out right, then I'd try to go back and find my mistake. I'd look for sign errors first, because that's the most common. But if it doesn't check, then go back and fix it. So x is 2, y is -5. Writing is the coordinates of the point, and we are done with that. Okay, now, I think those are lots of fun. I hope you will too. Part B has really nothing to do with that, though. So I guess it at least gives you a break from it. For Part B, we are finding the area of an isosceles triangle. All right, so pretty much we're just going to do one example of this. So, this is example 4 from the book. It's only the third one in the note, but I'll put 4 because it'll match example 4 in your book. And basically, we're just finding the area of a triangle. Find the area, well, obvious it's going to be of a triangle because here is our triangle, and it's supposed to be isosceles. Try to make it look like it is. All right, there's my supposed to be isosceles triangle, and this is 4 centimeters, this is 5, and this is 5. All right, well, we know that to find the area of a triangle, you take 1/2 times the base of the triangle times the height of the triangle. They did not give us the height of this triangle, so we need to figure it out for ourselves. Okay, the way you do that, if we were to drop a perpendicular line from this angle to the opposite side, okay, perpendicular, it cut this triangle into 2 right triangles. Okay, and we have a very special theorem for right triangles, and that's the Pythagorean theorem, a squared plus b squared equals c squared, that we can use to find the height. So I'm just going to redraw 1/2 of that. Okay, so this is the height we're looking for. This is the 5 centimeters. Now, this is half of that base, so it's 2 centimeters. Okay? And then what we're going to do is Pythagorean theorem. So that is a squared plus b squared equals c squared. 2 squared plus the height squared. Remember, c is always the hypotenuse, which is the longest side, is always opposite the right angle. So that's 5 squared. All right. And now that's 4. 4 plus h squared equals 25. Subtract 4 from both sides. The height squared equals 21, which means the height is the square root of 21. That does not come out even. It also doesn't simplify, so that's actually nice for us. It's a little less work. Then we use our area formula. Area equals half the base times the height. All right, and that's of the original triangle. So the area is 1/2 the whole base, 4, times the height, which we found out is the square root of 21. Half of 4 is 2, so the area is 2 root 21. You don't need to get a decimal answer to this, just leave it like that. I'm going to want to see this, so don't just do the whole thing on your calculator and only give me a decimal. I want to see this. If you want the decimal also, go ahead. But this is the exact answer. Decimals are going to be rounded. And our units were centimeters. We're doing area, so those units are squared. That's all there is for Part B, and that's the end of Lesson 13 notes.